Thank you. Hello, everyone. I'm Henrich, a security engineer from TrailBits, and today I will tell you how we managed to leverage LLVM analysis in our MLIR toolchain. To give you a bit of background, at TrailBits we are developing an MLIR-based front-end for C and C++. It is publicly available on GitHub, or you can also try it on Compiler Explorer. The main motivation behind this new front-end was that we do a lot of analysis for which it is often useful to have more high-level view of your source code. So we use for that an MLIR, and we start representing the source code in between AST and all the way down to LLVM. So as we are generating the MLIR, we generate some high-level dialect, some low-level dialect, and all the way to LLVM dialect down at the bottom. And in the future, we plan also to integrate Clang IR in these steps. And on top of these dialects, we can also build new abstractions which we can use further. However, there's a lot of cool LLVM-based tools in the wild, which we do want to use also on our MLIR representation. But how can we achieve that? We need to somehow lift the LLVM analysis results back to our MLIR representation to do so. For that, oops. Can somebody accept that? To do so, we created something called Tower of IRs, which is a structure of all the modules or all the modules we encounter during the code generation. So as we are generating the MLIR in our code gen, we make a snapshot of the modules. And the second ingredient in this Tower of IRs is that we keep also the provenance links to traverse back to the Tower of IRs. So using this, you can then walk down from high-level representations all the way to LLVM, and also use provenance links to link the low-level information with some high-level representation. So in a way, we have a bidirectional map between MLIR modules in this way. So one can say that we created the real multi-level IR in this way. We don't need to keep all the MLIR modules we encounter during the code gen, as this will be really memory consuming. We can just keep the snapshots that are interesting for our analysis. In this way, we can just have some high level or low level stuff and so on. In VAST, we don't have just 3 layers, but we have a lot of them. We are trying to be as fine-grained as possible. So you can see we do a lot of type lowering and ABI lowering, variable lowering, and so on. And after each transformation, we can make a snapshot that can be used to link the information in between these transformations. And how do we actually create a snapshot? We use the pre-existing MLIR tooling for that. This allows us to take the module, put the snapshot into a file, and transform the locations to point to this new representation. So we use the MLIR locations, which are mandatory in the representation, to keep the provenance information to the previous module. So in this way, we can then use locations to traverse back to the previous MLIR modules we encountered. So let me demonstrate this on this simple example. We have some arithmetic here on today's integer sequence 10, 4, 24. And let's say we want to perform some dependency analysis on this program. For that, we need to first lower to the LLVM IR. So we start from AST and lower to our high-level representation. This basically is one-to-one mapping to the AST. Here you can see the representation of the statement on the 4th line. There is some variable declaration, reference to B, multiplication, and so on. And also we have here the location that points to the original source. For the readability, I will keep only the locations at the last line, but MLIR keeps a location on each operation of the sources. Further, we started lowering to lower representations, so we lower types. In here, you can see that we lowered high-level types to some standard types in the MLIR, so we have signed integer 32, and we already can use these two layers to relate high-level types with low-level standard types. And in here, location already points to the high-level dialect, not to the source. Further, we lower to other layers. In here, we perform some ABI lowering or function lowering, which does not really influence this example. So these are actually candidates which we can omit during the snapshotting. And we can skip this snapshot or just keep some identity maps between the modules. Later, we lower variables to our low-level dialect. Further, we lower to variables to our low-level memory representation. So we already have some allocations and stores and loads. And at each step, we still point with the locations to the previous layers. And lastly, we reach LLVM dialect, which has the computation that you would expect for this statement. From here, we generate the LLVM IR. This is for the entire program. The red part corresponds still to the fourth statement. And in this last step, we need to keep additional map between LLVM IR and MLIR, because now we don't have the MLIR infrastructure to do the mapping. And now we reach finally the point where we can do the dependency analysis. So let's say we want to ask at some high level, what other statements is this statement for dependent on? So for that, we lower down, and we know only this for instructions corresponds to the statement, and we run the dependency analysis, and we find out that the store in the blue is the dependent operation for the statement. And this actually corresponds to the B that is used in the statement. But how do we relate now back to the top? We can use locations for that. So we backtrack to the tower from bottom up. We know that store corresponds to LLVM dialect, that corresponds to our low-level dialect. We can go there to high-level dialect and all the way back to the source. And we can use this information now at arbitrary locations in the tower. We can use the dependency analysis at some low-level representation, or we can also use the information in the high-level representation. And as you can imagine, this can be used beyond vast. You can use it in arbitrary MLIR toolchain. You can just perform snapshots as you are translating your MLIR modules and use just locations to point in between these modules. But one needs to be cautious about how aggressive their transformations are, as if you do too complex transformation, it might be hard for your analysis to relate the information between the two modules. As it is always up to the high-level analysis and the user how they will interpret the locations from the low-level representation. So to conclude, we were able to leverage LLVM-based analysis in our MLIR toolchain using a so-called tower of IRs. This was based on snapshotting the MLIR along the way to our low-level representation and using locations to backtrack the information up. This work is publicly available on our GitHub, and you can also see it on the Compiler Explorer, but at the moment you can only visualize single layer, as there's only capability to see single module, and we are working on the technicalities how to represent the entire tower at the Explorer too. Basically, we want to showcase the module of modules in the Explorer for the analysis. And if you have any questions, you can reach us tomorrow at the poster session to ask for this stuff. Thank you for your attention.